All right, 15.6 part 2. So for the second part of 15.6 video, I'm going to do a couple of examples. Okay, the first question is example 4 from your book, and it's a double integral of x plus z ds, where s, your surface, is the first octant portion of y squared plus z squared equals 9. Okay, so looking at what we did just in the first video, here's a simple line integral, a line integral of a vector field, a simple surface integral, and then a surface integral of vector field, or flux. Okay, what we're doing here is not flux. We're just doing a simple surface integral. We've got a function times your ds. Okay, so we've got our function x plus z times your ds. And we've got the first octant portion of this surface. So this surface, that's just a cylinder whose axis is the x-axis. So let's do this. We've got the x-axis, the y-axis, and the z-axis. Y squared plus z squared equals 9. Y squared. Okay, so we've really got a circle in this direction with a radius of 3. 1, 2, 3. And we just want the first octant portion, so that's where x, y, and z are positive. And then your x is going to go from 0 to 4. So here, you're going to get this like this. So we've got this sort of a shape here. And this right here is your surface. Okay? Now, in order to define this surface, there's a couple ways that we could do it. We could define the surface. We could define z as a function of x and y. We could do that. Okay? Or we could define y and z in terms of, really x, y, and z in terms of any two parameters we want. So I would suggest x would just be x, or we could call it u if we wanted, but we could just call it x. Y and z, well, with y and z, these make a circle. So we could call y r cosine theta and r sine theta. On this surface, your r value is a constant at 3. So 3 cosine theta and 3 sine theta. Okay, so we could define it that way. So we've now defined our surface. So let's define our surface in terms of u and v, or in terms of our two parameters, which are going to be x and theta. So our x is simply x, our y is going to be 3 cosine theta, and our z is going to be 3 sine theta. Okay, so that's how we're going to define our function. So now we go back up here, and we've got the double integral of x. Well, x is just x, plus z. Well, z we've defined as 3 sine theta. Okay. And then the ds, well, remember what the ds, it's representing one tiny little parallelogram, one tiny little section of our surface, which is going to be typically be our u cross r v, but in this case it's going to be r x cross r theta dx d theta. And this is going to be nice because we know x goes from 0 to 4. And theta is going from 0 to pi over 2. So we only want to go 1/4 of the way around the circle. Okay? So we have to figure this out. So I'm going to go over here and I'm going to do Rx, which is equal to the x derivative of our surface is just 1, 0, 0. The theta derivative is going to be 0, that's going to be negative 3 sine theta and 3 cosine theta. Okay, so we want to find our x crossed with our theta, which is going to be I, j, k, at 0, negative 3 sine theta. Sorry, I did that wrong. Okay, the Rx is going to be 1, 0, 0, 1, 0, 0. The R theta is going to be 0, negative 3 sine theta, and 3 cosine theta. Okay, so this is going to be equal to, in the I direction, you've got 0 minus 0. In the j direction, you've got 3 cosine theta minus 0. But it's negative because it's the j. In the k direction, you've got negative 3 sine theta. So the magnitude of our x crossed with our theta is going to be the square root of 9 cosine squared theta plus 9 sine squared theta, okay, which is just the square root of 9, which ends up being 3. Okay, so the rx cross r theta, when we go put that up in here, that's just going to be a 3. So we've got double integral of x plus 3 sine theta times 3 dx d theta, double integral, let's distribute that 3x plus 9 sine theta dx d theta, x goes from 0 to 4, theta goes from 0 to pi over 2. Okay, we take the antiderivative with respect to x, so 3x squared over 2 plus 9x sine theta from 0 to 4. So that's going to be 3 times 16, 48 divided by 2, so 24 plus 36 sine theta. Integrate that with respect to theta from 0 to pi over 2. We get 24 theta plus, actually that's going to be a minus 36 cosine theta from 0 to pi over 2. So we get 24 times pi over 2 minus 36 times cosine of pi over 2, which is 0, minus, and we'll plug in 0, 24 times 0 minus 36 cosine of 0 is going to be 36. So we get 12 pi plus 36. Okay, and that is the answer for example 4. Okay, so let's move on to example 5. So example 5 says we want z equals 4 minus x squared minus y squared. That's our surface, and that's a paraboloid opening down, starting at 4, and then it comes down this way, so our circle in this direction is going to be at 2. Okay, and now we want to find the flux. So for this one, we're actually finding, what does it say? Find the rate of mass flow through S. So we're finding, if this is our vector field, and you see, if we're in, let's say, the z to be 4 minus x squared minus y squared, the question says a fluid of constant density rho is flowing through the surface according to this vector field right here. And they said it also has an upward unit normal vector. Since this is an open surface, notice this base of the surface is not given, we would need to know if we're going upwards, the flow going up, or going downwards. Okay, when not given, the natural orientation is always upwards, but they do tell us that in this case. Okay, so what we're doing is we're finding the double integral of our f, and they give us a constant density, so we're going to put that rho density here with the f, dotted with your unit normal vector over our surface. Okay, so our r of, when we can find this surface, we can parameterize in terms of x and y. Okay, so the x is just x, the y is just y, and the z is going to be 4 minus x squared minus y squared. Okay, so this is the case of the simplified version. Okay, so remember, for flux, if we look at our chart, for flux here, there were these two. We would do f dotted with this cross product. Or if z is a function of x and y, we could do f dotted with opposite dg dx, opposite dg dy, and 1. Okay? Which is the one we're going to do here. Okay? So we've got our constant. This is a constant density, so we can actually pull that out. And our f is going to be x, y, z. Okay? And then we're going to dot that with the normal. With the normal would be rx crossed with ry, which comes out to be the opposite of dg dx, opposite of dg dy, comma 1, dx dy. Sorry, that should be a double integral. Okay, so let's do this first, and then we can figure out how to move forward. So we've got x times the opposite dg dx. Well, dg dx, let's do g sub x, the x derivative of our z value is going to be negative 2x. dg dy is going to be negative 2y. Okay, so we've got, actually let's do this, x, y, the z value is 4 minus x squared minus y squared, because at this point we want everything in terms of just two variables, two parameters. Opposite of dg dx, well dg dx is this, opposite of that is going to be positive 2x. Opposite dg dy is going to be positive 2y and 1. dy dx dy or dy dx. Okay, so we've got rho times the double integral. We've got 2x squared plus 2y squared, and then plus 4 minus x squared minus y squared dx dy. Simplifying, we're going to get rho. We've got 2x squared minus x squared is x squared. 2y squared minus y squared is y squared, and then plus 4. And then we've got dx dy. Now, if we project this thing onto the xy plane, we've got a circle with a radius of 2. Okay, so I'm going to turn this into r dr d theta. I've got rho of x squared plus y squared. Well, that's going to be r squared plus 4 times r dr d theta. Okay, now r is going to go from 0 to 2. Theta goes from 0 to 2 pi. We can continue from there. So rho times the double integral of r cubed plus 4r dr d theta. Okay, r goes from 0 to 2, so that's going to be r to the 4th over 4 plus 4r squared over 2. So 2r squared from 0 to 2. Okay, so we're going to get 16 over 4, 4 plus 2 times 4, 8. And then minus 0, so we get 12. And now I want the integral, 0 to 2 pi of 12 d theta, which is going to be 12 theta from 0 to 2 pi, so 24 pi times rho. And that should be our answer. Okay?